Hello. Welcome to this webinar. My name is Daniel, and I'm the CEO of ETN. I think we'll just give it a couple of minutes, or at least one more minute before we start start the webinar. Please feel free to use the Q&A or chat module if you have questions during the webinar, and we will make sure to answer all of your questions. Great. Seems like many of the people already has joined. I think I'll just give it one more minute before we get going. Perfect. All right, I think I'll just start with a short introduction. My name is Daniel Kumar. I'm the CEO of ETN. ETN is the company that has commercialized the EME device, and I'll share a couple of slides about the company also. And together with me, we have Professor Stig Pedersen-Bjergaard. He is the inventor or the co-inventor of EME. So I'm really glad to have him here today to host this webinar. The plan is to have around 30 minutes of presentation and then 15 minutes Q&A. So yeah, feel free to ask questions and take notes. And of course, if you have any other questions afterwards, don't be afraid to send it to me. So very briefly, ETN is the company that was established in 2013 in order to commercialize the EME technology. We did that last year, where we launched the instrument at the Analytica in 2024. And the goal of the equipment was to standardize EME so you can use it all over the world, and it's easier to see how different results actually works. We have sold the instruments now to 4 European countries, and the instrument itself look like this. It's a device that can do 12 extractions at a time. And we have designed this instrument so you can set different voltage on each extraction cell. So this is a great tool for method development, R&D, but also for low throughput applications. The consumables we have, and that Stig will talk a bit about, is we have 2 types of vials, giving you the opportunity to do enrichments. We have the membrane, the physical membrane that you can see on the picture, and we have the union that connects the vials and the membrane. And just to say it, our goal is to launch the 96 well format by the end of Q2 next year. So this is a good way to get to know the EME technology, to develop methods, and then if you're interested in higher throughput applications, you at least know that this can be a great tool in the future. And just the last slide from me is that we have a couple of EME days in June. So this will be a full day of a seminar and also practical training. The first one will be in Germany, and the second one will be in Oslo. So if you are interested in actually testing the instrument and to get a deeper knowledge about EME, I would recommend you to contact me and yeah, participate on these ones. We will have EME days also in the fall and winter, but this is the one that's set for now at least. So that was my 2 minutes, and now I will leave the word to Stig.
Ja. Good morning, ladies and gentlemen, and welcome to this webinar on electromembrane extraction, or EME. EME is a new and green microextraction technique for bases, for acids, and for ionic compounds with permanent charge. And extraction in EME is driven by an electrical field. So my name is Stig Pedersen-Bjergaard. I'm working at the University of Oslo and also at the University of Copenhagen part-time. And together with Knut Rasmussen, my former colleague, I'm inventor of EME. So in EME, analytes of interest with charge, in this case here, positively charged substances in an aqueous sample is brought in contact with a liquid membrane, which is a thin film of organic solvent. And on the other side of this organic liquid membrane, we have the acceptor solution. It is an aqueous buffer, and the extraction process is then driven by an electrical field sustained across the membrane, in this case with a negative electrode in the acceptor solution for extraction of positively charged analytes. The liquid membrane is that separates the acceptor and sample solution is a key element in EME. And the liquid membrane is prepared by pipetting a few microliter organic solvent into a porous hydrophobic membrane. And you can see the dry membrane here. And when we have pipetted the organic phase, it becomes like this. It becomes more transparent. And the organic solvent, when we pipette the solvent to the surface of the membrane, it immediately goes into the pore volume, and it's immobilized and held there by capillary forces. The first experiment on EME was conducted in 2004 in our lab. You can see the equipment here. Here is the extraction cell. You can see the electrodes. You can see the connection to the power supply, and agitation of the sample is important in EME. So here is the agitation system. This was back in 2004. Since that time, we published the first paper in 2006 on EME, and since that time, more than 550 papers have been reported in the literature by many different groups around the world. Papers dealing with applications in areas such as pharmaceutical, environmental, and food and beverages analysis, but also extraction of heavy metals and peptides and many other different substances. There are also papers on fundamental aspects of EME, models for mass transfer, kinetics, and selectivity. And people had also been developing EME into different technical configurations, such as 96-well technology, and into microfluidic devices. A very important milestone in the development of EME was the launch of commercial equipment last year. You see the apparatus here. And the key feature of this system is that the sample is located in a small vial made of conducting polymer. The same is the acceptor solution. And in between, we have the liquid membrane. You can see the conductive polymer vials here, and you can see the membrane, which is inserted in this union, and by such is located between the sample and acceptor. And the nice thing here is that the electrical field is coupled directly to the containers because they are made of conducting polymer. So the containers also work as electrodes in this system. So why we have been working with EME for such a long time and try to develop this idea and technology? Well, first of all, when we do the extraction, we use only a few microliters of organic solvent per sample. So we can do extractions very green and very sustainable. People at my age, they are used to buy bottles of organic solvent, but the next generation laboratory managers, they are currently in the ground school now. They will care much more about greenness and sustainability, and they will use the green analytical chemistry methods. Another advantage of EME is that we extract the analytes of interest from a sample into aqueous acceptors. So it means that the acceptor solution can be injected directly into liquid chromatography and or LCMS after extraction without any need for evaporation and reconstitution in mobile phase. Another thing is the selectivity and cleanup efficiency of EME, because in this system here with the negative electrode in the acceptor, we extract basic compounds from the sample solution through the liquid membrane and into acceptor. Compounds that are highly polar or water soluble, they will remain in the sample because they cannot penetrate the organic solvent. Acids will also remain in the sample because they are electrophoretically moving in the opposite direction. Very hydrophobic substances that are neutral will accumulate to some extent in the membrane, and only in this case bases within a certain polarity window will be extracted into the acceptor. So by this we get very high selectivity and very efficient cleanup. We can extract from a relatively large sample volume and into a much smaller accepted volume, and by such we can do enrichment. And the selectivity in the system we can tune by multiple parameters. We can tune the selectivity based on the direction of the electrical field. With the negative electrode in the acceptor here, we will extract bases, but we can reverse the voltage and extract acids. We can also play around with the magnitude of the electrical field. I will come back to that because that controls selectivity. We can play around with the chemistry in the liquid membrane, and this also had huge impact on the selectivity of the system. And of course, pH in the sample and in the acceptor also determines selectivity because pH determines the ionization of the different compounds in the sample. There are, of course, also limitations, and the limitations of EME currently are especially acids, but also to some extent bases with very high polarity. So if they have very low log P values, they are difficult to extract into the liquid membrane. We can extract most of them, but current liquid membranes we use are not super stable in contact with complex samples for the very, very polar analytes. Then I will show you some examples of methods just to understand how the chemistry work and also what type of performance level we can expect from EME. And in the first case, we are to extract fluvoxamine from plasma samples. Fluvoxamine is a basic substance with log P close to 3, and it's a base, and we are to extract this from human plasma samples. To build up the method, we need to define the chemistry of the chemical composition of the liquid membrane. We need to define the sample and also the sample diluent, because normally we dilute the sample a little bit with buffer to control pH in the sample. We also had to define the acceptor. We had to define the voltage, the magnitude of the electrical field. We need to define the extraction time and the agitation rate. In this case, with fluvoxamine as the analyte, which is a relatively nonpolar base, we normally choose 2-nitrophenyl-octyl ether, which is this liquid here, and we normally use 8 microliter of this solvent as the liquid membrane. We have found out by many experiments over the years that nitrophenyl-octyl ether, or NPOE as we abbreviate it, is definitely the first choice liquid membrane for bases of low polarity. And with 8 microliters, we fill up the entire pore volume of the support membrane. So we have a very nice liquid membrane in this case. Sample, in this case, we pipette 125 microliter plasma into the sample vial, and then we add a similar volume of formic acid to acidify the sample to make sure that the analyte is fully protonated in the sample, because it needs to be fully protonated in order to migrate in the electrical field. And with the vial, the fill volume is then 250 microliter in total, which is an appropriate filling level for the vial. If the vial is completely full, the extraction efficiency is lower because we get poor convection in the sample when we agitate it. And if the filling level is too low, then the liquid does not come in contact with the membrane. But 250 microliter is an appropriate volume. Acceptor, we use also here the same formic acid to make sure we have acidic conditions also in the acceptor solution. So analytes are protonated. And when extraction is finished, we can inject this acceptor directly into the LCMS system. So it's fully compatible with the LCMS system. The voltage, in this case, we will apply 100 volts. You can see how the extraction efficiency is dependent on voltage from this figure. And if we have no voltage, we have no or almost no extraction. And you can see the extraction efficiency increases rapidly with voltage. And in our case, we select 100 volts. It's a little bit higher than, or we could use lower voltages, but then the extraction kinetics becomes a little bit slower. So therefore we selected 100 volts in this case. The extraction time is set to 15 minutes. Here you can see how extraction recovery varies with extraction time, and you can see that to really get the maximum recovery, we need to extract for half an hour. But in our case, we finished after 15 minutes. We are close to equilibrium, and we finished here to keep the extraction time as low as possible. Agitation was set to 800 rotations per minute, and agitation is important for the extraction efficiency. So we need to agitate the sample to get convection in the system. And with this method, we can extract with recoveries of 92% for fluvoxamine. We can get up to 100% if we extend the extraction time to half an hour. But as you can see, we get exhaustive or near exhaustive extraction, and we get linearity when combined with EME with LCMS in the concentration range you can see from the table. Very nice linear correlation and very high level of repeatability. And this value here is mainly due to the fact that we now are using EME equipment, which is of industrial standard. So we can do the extractions very repeatedly. If we compare the EME method for fluvoxamine with the standard procedure they use at the University Hospital in Trondheim, Norway, you can see that the consumption of organic solvent is much lower with the EME Both methods use a small volume of formic acid. The protein precipitation method used nitrogen gas for evaporation of organic phase. This is not the case in EME because EME is just extraction, and then the extracts can be injected directly into the LCMS system. Whereas with protein precipitation, you first precipitate the proteins, then you filter, then you evaporate the liquid, and then you reconstitute in mobile phase. And all this takes longer time than just EME for 20 minutes. So both in terms of chemicals and in terms of time, EME is favorable. I would like to show you one second example, and in this case it's salbutamol, which is the pharmaceutical substance we are to extract. And now the log P value is close to 0, so we are dealing with a more polar substance in this case. And if we try to use NPV, nitrophenoloctyl ether, the same liquid as we used in the first example, if we try to use this for this substance, we will not be able to extract the salbutamol compound because it's too polar. And actually, with NPV, we have a extraction window for bases between log P2 and log P6. You can see from this figure here, we have plotted recoveries for 90 different pharmaceutical substances, plotted their recovery as function of their log P. And you can see all the very polar compounds up to log P2. They are not extracted because they are too polar to enter the liquid membrane. Then you can see from log P2 to log P6, most of the basic pharmaceuticals are extracted with very high recovery from plasma. And then you can see the very hydrophobic substances, they are extracted with low efficiency because they are trapped in the organic phase in the liquid membrane. So NPV has an extraction window from log P2 to log P6 approximately. The interesting thing is that we can decrease the size of the extraction window by decreasing the voltage. Or we can increase the voltage and then we can expand the window so it goes over a wider log P range. We can use a liquid which is more hydrophobic than NPV, and we see that the extraction window shifts to higher log P values. Or we can use a liquid membrane which is a little bit more hydrophilic than NPV, and the extraction window shifts to lower log P values. Or we can add an ionic carrier to the liquid membrane, and we get ionic interactions in the system, and by such we can move the extraction window into the very polar substances. So therefore, to extract salbutamol, we use another liquid membrane, which is composed of 6-methylcoumarine mixed with thymol. Those two are solids, but when they are mixed together, they form a deep eutectic solvent. We combine this deep eutectic solvent with undecanone, and then we add a few percent of di-2-ethyl hexyl phosphate. This is an ionic carrier, and it facilitates the extraction of polar substances. So this membrane is the first choice liquid membrane for bases that are highly polar. With this new membrane, we use, again, formic acid as acceptor. We reduce the voltage a little bit compared to the previous example. So now we extract at 40 volts. And by these conditions, we can extract salbutamol with a 77% recovery. Again, high repeatability, and extraction time in this case is 30 minutes. We should then look a little bit into applications. And first of all, I would like to show you this window because this is the molecular window of EME so far. So we can predict, or extraction in EME is related to the hydrophobicity of the substance, the log P value. So we have log P on the x-axis, and it's also dependent on the charge of the analyte. So we have charge on the y-axis. We have developed robust and generic systems and methods for bases from approximately log P minus 2 up to log P plus 6, bases with charge plus 1 or plus 2. And in similar way, we have very nice and robust generic methods for acids with charge minus 1 or minus 2 from approximately log P 0 up to log P 6. In the rest of the diagram, we have been extracting compounds down to minus log P minus 7. We have extracted basic substances with charge up to plus 5 and down to minus 3. But in this light green area, I would say that robust systems are under development. We can do extractions here, and we extract many compounds also in this region. But when they become very polar, the current systems are less stable, and we are continuously developing new membranes to address more or to expand the more robust methods into the difficult or to the polar compounds. The substances we are dealing with are all with molecular weight less than 2,000 Daltons. A few examples from literature. Here is one recent application where volumetric absorptive microsampling was combined with electromembrane extraction for extraction of doxorubicin from whole blood samples, just to give you one idea of how we can use EME. Doxorubicin is both an acid and a base with log P 0.8, so it's efficiently extracted by EME. Another example you see here is determination of alkaloids in acute poisoning by electromembrane extraction. So here, colleagues from China have extracted alkaloids. They are bases with medium polarity, and they have been extracted from whole blood. Here is another example where endogenous metabolites in human plasma has been extracted by EME. Those are, in this case, a basis of high polarity. Here is another example where bases and acids in the log P window from minus 6 up to plus 7 have been extracted from cell culture media, and they have characterized the cleanup of EME very nicely. So here is another paper now looking into food samples, where we have been looking for veterinary drug residues. So in this case, it's basic substances from log P minus 7 to log P plus 6. So now we are more moving into food chemistry. Here is another food chemistry paper where heterocyclic aromatic amines have been extracted from Stig samples. So these are bases of low polarity. Here is another example where dialkyl phosphates have been extracted from urine samples. Those are acids with medium polarity. And also quicksilver has been extracted. So several heavy metals have also been extracted by EME. This is one example, this paper from Journal of Food Composition and Analysis. So there are many examples in literature. These were just a few examples just to give you a flavor of what is going on and what type of analytes and what type of samples we can use EME for. Cleanup is very important, and from plasma samples we are always concerned about proteins. But proteins are totally removed by EME. You can see here is a gel SDS page electrophoresis of acceptor solution after EME, and you can see it's completely free from proteins. So the proteins, they do not pass the liquid membrane, and they remain in the sample solution. We are also often concerned about phospholipids when we are dealing with plasma. And here you can see a phospholipid chromatogram after protein precipitation of plasma, and you get a huge amount of phospholipids in your supernatant that is then injected into the LCMS system unless you do phospholipid removal. But phospholipids they are removed by EME, because you can see the red chromatogram here is a similar chromatogram looking for phospholipids after EME in the acceptor phase, and you can see it's totally free from phospholipid. So the phospholipids remain in the sample or are trapped in the liquid membrane and does not enter the acceptor solution. I will finish off just saying a few words about the commercial equipment and how to use it, just to give you a flavor of the system. Here are the conductive vials that are used for EME. We have a large vial that can hold 200 to 500 microliter liquid, and we have a small vial that holds 30 to 150 microliter. It means that if you use this one as your sample vial and fill it up to 500 microliter, and you use this one for the acceptor and fill 50 microliter acceptor solution, then you can pre-concentrate by a factor of up to 10. The vials are connected by this union, and the support membrane for the liquid membrane is placed in the union. So you get like extraction cells like this with sample, membrane, acceptor, and you can place 12 such samples in the 12 position holder of the instrument, and then you can, when you close the lid, the electrodes here, they come in contact with the conducting polymer, and by such the electrical field is coupled into the system. This 12 position holder is on top of the instrument, as you can see here, and the rest of the instrument is an agitation unit, because all the samples are agitated during extraction. And everything is controlled from computer software. To do the extraction, you first load the union that connects the two vials. You load the membrane, the dry membrane, the support membrane there. Then you fill acceptor solutions into the vials, and you fill sample solutions into the vials. Then you put on the union with the membrane on the acceptor vial. Then you load the organic phase, a few microliter of NPV or another solvent immiscible with water is pipetted onto the membrane, and you get this liquid membrane. You can see here is the dry membrane, here is the immobilized liquid membrane. And in a few seconds after you have delivered the organic phase, the membrane is ready. Then you connect the acceptor and the sample solution. You load the extraction unit into the 12 position holder, and you close the lid and turn on the extraction. During extraction, we always measure the current in each extraction cell as function of time. That gives us a very nice diagnostic tool to see if everything goes well in each of the samples. And when you have finished, you just cap the acceptor vial and insert it into the LCMS system, and it's ready for analysis. Okay, that was all. So thank you for listening.
Thanks for the presentation, Stig. Do we have any questions from the audience? If not, yes, Bo. Now your microphone is, you have the possibility to use the microphone, Bo.
I think he is muted. His microphone is muted.
Yeah, otherwise you can also write it in the chat. It seems like he's typing. You should have the opportunity to use the microphone now. Otherwise, you can just also write the question on the side. While Bo is writing the question, I can also just share just a couple of things that can be relevant for you. And we have this website called howtoeme.com, where you can type in analytes of interest. And based on the generic systems that the University of Oslo has made, it can give you an answer if EME is suitable for the analyte of interest. And we have several application notes that you can find on the top of the page, giving you quite good descriptions on the membranes, the LCMS systems, and all the data you need in order to perform EME and what kind of results you will get. On our websites also, we have quite a few generic methods and documentations and publications. So I just wanted to say that. Here's the question from Bo. Do you want to take it, Stig?
Yeah, can I see it somewhere?
Yeah, if you click on the chat button in the top, the question is, I missed the part why the membrane is important for separating analytes with a different log P. I thought they were only used for filtering particles. And the second question is it possible to process larger volume samples, such as concentration of water samples?
Yeah, so the first the membrane is, well, the support membrane is actually a filter membrane, but then it's soaked with organic solvent or you can say oil. So it is not a filter membrane then, but it's an oil membrane. And so if compounds are very polar, then they have difficulties to pass into the membrane because it's organic. So that's why very polar substances are not extracted unless we put ionic carrier into the membrane. If compounds are of medium polarity, they go into the organic membrane, but they also go out again on the backside and are recovered in the acceptor phase. Whereas very hydrophobic substances, they go quickly into the membrane and then they tend to stay there due to hydrophobicity. So therefore, the liquid membrane extracts in a certain hydrophobicity window or log P window. Processing larger samples, well, with the commercial device, I think the maximum volume is 500 microliter currently. But people have been working with EME from larger volumes in the literature, but this has been done in home-built systems. So the limitation with the commercial device is about 0.5 milliliter for the sample volume.
Yeah, so I could just add that, of course, if we see the interest from the industry to do larger, for example, water samples, it will be possible to make commercial systems for that also. So we have just been focusing now more on the clinical side and food and environmental analysis that requires smaller sample volumes. But basically, the principle is the same, and you can just kind of make the dimensions bigger. We got a question also from Donald. Thanks for the question. How would you prepare a solid sample, like a food commodity, for example, starting the EM extraction?
So then we had to homogenize the solid sample in aqueous solution, or that can be in water or in acid or in base, depending on the solubility of the substance. Or we can also use a weak acid or weak base in water, but mixed with some methanol or other organic, polar organic solvents if that is required. But of course, the content of organic solvent cannot be 100% in the sample, because then it might challenge the stability of the liquid membrane.
Yes. We also have one more question. Can you separate heavy metals from ionic lipids?
We can extract heavy metals. There are several papers in literature reporting that. From ionic lipids, it depends on if the sample must be soluble, or the lipids must be soluble in some aqueous matrix. So it's a difficult question to answer right on.
But this is something, Christopher, that you can, if you have some concrete questions regarding this, we can look at this also after this webinar. We have 2 more minutes. Is there any other questions on top of your guys' minds? Otherwise, I will just use the opportunity to thank all of you guys for participating in this webinar, for Stig to host the webinar, and just a quick reminder that we will have EME days. So if this is interesting and you want to get a tutorial and test how the instrument actually works, we have the one in Germany, June 3rd, and in Oslo, June 5th. So thank you very much, and hope to see you again soon.
Bye bye.
Bye.